Chapter 5 deals with uniform circular motion, uh, and uniform circular motion is the motion of an object moving around a circular path at a constant speed. Okay, so here we go. We've got a person twirling uh, some mass, let's call it a ball, on a string, around and around in a circle, and we're going to say that she or he, whoever's swinging this thing, is moving it at a constant speed. Uh, One of the things, in order to analyze this, let's analyze what what the speed is. So how would you solve for constant speed? Well, we know that average speed simply is distance over time, some form of distance over time. We would write that as average speed equals distance over time. Uh, the distance that this object is moving, if you follow my pointer, is the circumference of the circle. Distance is circumference. And how do you get the circumference of a circle? Circumference equals 2 pi r, where r is the radius of your circle. So we can take this for and substitute it in for our distance for the circular motion. And our equation becomes average speed equals 2 pi r over t. Now, the time that it takes to make one revolution is the time we're interested in. And we define that as something different than just the lowercase t you've been used to. Because if we time this and we keep spinning and spinning and spinning around in a circle, uh, we would see our speed drop, even if we were, you know, moving at a constant speed. If you just timed this and just spun it around in a circle multiple times, you really wouldn't we wouldn't be talking about this t. The time that we are specifically interested in, we define as the period. And again, that period is the time it takes to make one revolution around the circle. We define period, we label the period with a capital T for period to distinguish it. And in order to get the actual period, the time it takes to go around in a circle, there's a number of ways you can do that. You can time how many times it takes to go around and around and around, and what you would come up with is what we define as a frequency. And time, or the number of times per uh, the number of repeating occurrences uh, over a given amount of time. And that frequency is often defined in hertz. To get the period, you take 1 over the frequency. Uh, 1 over frequency, and I'll explain that a little bit further. But this period is what should be in here for time. So average circular speed is equal to 2 pi r over the period. And just briefly, frequency you've probably heard given in units of hertz. So if I had something spinning around 33 hertz, what a hertz is a unit of 1 over s seconds to the negative 1. I'm sorry, 1 over second. So the period, so what this is saying is there's 33, this person's spinning this uh, 33 times in a given second, 33 times per second. So the period is 1 over 33, or 0.0303. And if we're taking 1 over hertz, or 1 over s, we get seconds. So the period has units of seconds, like it should. And what that's telling you is it takes 0.0303 seconds to make one complete revolution. And that's why the period is important for getting our constant circular speed. Now, what we need to understand is when we're describing the velocity vector, remember velocity is the vector component of speed, we may have the speed from before, but when we talk about the velocity, we need to understand that the direction of the velocity is changing, even though the magnitude is not. Again, the direction of the velocity is changing, even though the magnitude is not. And if we looked at a circle, if we took ourselves and drew a circle, uh, you would note that if we showed the velocity here, at any given point on the circle, the velocity vector is going to change its direction as it goes around and around in the circle. So your velocity is constantly changing as it goes around. And we know that change in velocity over time is described as acceleration. So therefore, even though you have a constant speed going around the circle, there is still acceleration. Okay? And this acceleration uh, is directed towards the center of the circle, and we call this centripetal acceleration. Centripetal stands for center seeking. So this is center seeking acceleration. So it's directed towards the center of the circle, the centripetal acceleration. And the way we calculate that centripetal acceleration, we calculate that by squaring the magnitude of our velocity and dividing it by the radius of that circle. So if this is the radius of our circle, and we have our velocity here, square the velocity, divide it by the radius, and that gets us our centripetal acceleration. If you do a quick unit analysis, you'll have meter squared over second squared divided by another meter would leave you with meters per second squared, which is the units for acceleration. So just quick review, the magnitude of the centripetal acceleration is calculated using this equation. The direction is always towards the center of the circle, and if you notice, that acceleration is always going to be changing also. Okay, so velocity direction is always changing, and so is the centripetal accelerations always going to be changing as well. Now, moving along with how this relates to forces, when you have an accelerating mass, there's always a force associated with it. Something can't accelerate without a force, and we know this through Newton's second law of force equals mass times acceleration. We call this force that is related to the centripetal acceleration, obviously the centripetal force, the center-seeking force. It's in the same direction as the centripetal acceleration. So it too is center-seeking. And if we wanted to know what the centripetal force is, Centripetal force is calculated, obviously whatever the mass associated with it, and we're going to want the centripetal acceleration. Well, if we back up and think about what centripetal acceleration is, that's the velocity squared over r. So another way to write this equation, centripetal force is equal to the mass times velocity squared over the radius. One thing to note is the centripetal force is not some separate force. It's always the net force that's pointing towards the center of the circle. Sometimes it is a single force, such as tension. If you're going around, if you're spinning something in a circle with a string, you've got the tension that's acting as a centripetal force. Sometimes if you're going around, if you think about race car drivers, they go around banked curves, and in those cases, the friction is acting as the center seeking force, or perhaps force normal could also be acting as a center seeking force. If you think about the old uh, the carnival ride, uh, the centrifuge or the gravitron, sometimes it's called, it spins around and around in a circle, and then they drop the floor out, and you're stuck to the wall. Well, the center seeking force is the force normal that's acting on you. And a quick example of centripetal force, you've got a mass of 0.2 kilograms. It's moving around a circle. The circle has a radius of 0.6 meters, and we're moving at a constant speed. And we want to know what the tension of the string is. So we're assuming that there's a string attached to this mass as we're spinning it around. What's the tension of the string as it moves at 8 meters per second, and if we move it at 12 meters per second. So first, if it's moving at 8 meters per second, we have our force. Centripetal force is equal to mass times velocity squared over the radius. Well, we have all these things. We have the mass, we have the radius, and we have our velocity of 8 meters per second. And if we plug our numbers in, that's 0.2. 8 squared over 0.6. Our centripetal force is 21.3 newtons. If instead we spun this around at 12 meters per second, how would it change? We just substitute 12 in now for our velocity, and we get a centripetal force equal to 48 newtons. And please note that the relationship between the force and the velocity is going to be a parabolic relationship. So if we increased our velocity by, say, a factor of 2, our force would increase by a factor of 4. You can do that real quick by making this 24, and what's going to happen to the force? The force should increase by a factor of 4 if the velocity increases by a factor of 2. So 48 times 4 would be 192. So if my velocity was instead 24, we're saying our force would quadruple to 196. Run the calculations, put 24 in here, 24 squared times 0.2 divided by 0.6, you're going to get 196 newtons. So understand that relationship between the velocity and the centripetal force. If you increase the velocity, you're going to be increasing the force exponentially.